entertainment show here. That's good. Are you all set? Ready to get? Okay.
Okay. I think.
Thank you. Floor is yours.
Yeah, thank you. Hi, everyone. My name is Yang Liu, and I'm a PhD student at the University of Helsinki. And I'm happy to be here to talk to you about our paper, which used atom response theory to understand recommender systems performance. And this is joint work with my supervisors, Alan Medler and Dorota Glowacka. Let's first quickly recap the offline evaluation process. So given the datasets for each individual user in the datasets, we will calculate some evaluation metric, for example, precision at 10. And this is based on the top 10 recommendation given by a model. And we then take the average across all users to get an overall performance measurement. So this process is quite straightforward and widely used. However, in our experiments, we have run 47 to 51 recommender systems on 3 datasets. Surprisingly, we found that for many users, there are basically no positive atoms appeared in the top 10. This percentage of such users on movie lens is about 30%, and on Amazon books it's even worse. So with such high percentage, we think there's basically no discriminative power. Also, for these users who had nothing at top 10, basically this top N evaluation matrix failed to capture their user preferences. For example, we can see from this example, like this rank model must capture something because it ranks this positive atom at 11th, while this blue model performs much worse. However, top N evaluation matrix basically we cannot get such information from top N evaluation metrics. And also in recommender systems, we know that some users are hard to please. For example, we can see this blue user who likes almost all the popular movies, while this red user has some special taste, only likes time travel or time loop movies. It's natural to think that maybe recommending movies to this red user is more difficult than to the blue user. However, as I mentioned, the current framework take average across all the users doesn't account for user difficulty. And on the other side, it's similar, like some atoms are also difficult to recommend. But again, this framework still doesn't account for atom difficulty as well. So to deal with these problems, we seek solutions from atom response theory, which is a type of latent variable models used in psychometric assessment and educational testing. In IRT, basically, we will have a list of test takers and a list of test atoms. And each test taker will answer each test atom, resulting in such a matrix where each entry indicates whether this response is correct or not. So the basic idea of IRT is to extract some information from this matrix. For example, we can probably guess that this test atom 4 is more difficult than the test atom 1 because like fewer test takers can answer this question correctly. And on the other hand, we can also speculate that test taker 1 has better ability than test taker 3 because test taker 1 not only gives more correct responses, but also answers its challenging atom 4 correctly. So I hope from this example, we can see that IRT allows us to jointly model the difficulty of test atoms and also the test taker's latent ability. And basically, an IRT model is a statistical model, and so in the end, we need to estimate some latent variables. For example, we need to infer the latent ability for each test taker. And for each test atom, there are 3 parameters, namely atom difficulty, atom discrimination, and guessability. Atom difficulty matters how challenging it is to answer an atom correctly. So it is measured on the same scale as the test taker's latent ability. So basically, we can directly compare the ability of test taker and also the difficulty of the question. And discrimination measures how well an atom distinguishes between test takers. And guessability is basically just probability of guessing this question correctly. So in our work, we apply IRT to recommender systems. But in particular, we want to evaluate the recommender's ability in modeling user preferences, but based on the whole ranking instead of just top 10 atoms. We naturally model we naturally just take the recommendation algorithms as our test taker. And the most challenging part is that how to determine the test atom. And to frame this as a ranking problem, we adopt this pairwise comparison framework. And we create this user positive atom and negative atom triple as our test atom. So a recommender system is considered to give correct response if this recommender can rank this positive atom higher than the negative atom. And conversely, if the recommender predicts a wrong order, the response is considered incorrect. So with this formulation, we actually assess this model's latent ability to model user preferences. And this ability, more specifically, is defined as the ability to prioritize those higher preferred atoms over less preferred ones. We can imagine that if we use all triples, we actually model the entire ranking. However, even with the smallest data set we have, there are more than 5 million triples, and for each triple, we need to estimate 3 parameters. So you can imagine this is quite computational demanding. And therefore, we propose a sampling procedure to reduce the number of triples here. But due to time limits, please refer to our paper for more details. Just to match with our IRT illustration, here the test takers are the recommenders, and the user atom triples are the test atom. And after model fitting, we will opt the latent ability for each individual model. And for each triple, we will have 2 parameters, namely difficulty and discrimination. And you may notice that we omitted guessability here, because in our experiments, we found that the model can fit better without guessability. Also, in recommender systems, models' ability is not the only thing we care about. We also care about like users and atoms. So we kind of aggregate this a little bit to opt the difficulty and discrimination for each individual user atom, and also even the user atom pair. This is simply done by taking the average across all the triples containing an object of interest. About our experimental setting, we used 3 benchmark data sets out of different purposes. And we trained 51 algorithms on 2 movie lens data sets and 47 algorithms on Amazon books. And our implementation is based on RecBola, an evaluation framework for recommender systems. About our results, in our paper, we actually analyzed the recommender systems from 3 aspects, namely the recommenders themselves, their ability in modeling user preferences based on the 4 ranking. And also, we use difficulty and discrimination to analyze the test sets. We also assign test set information, which basically tells us, is there enough information to use this test set to determine, to make decisions like which model is the best. And in the end, we also have this qualitative analysis about atom difficulty and user difficulty. How does atom difficulty correspond to atom popularity, and how does user difficulty correspond to user engagement, things like this. But due to time limits, I'll just pick 1 highlight from each part here. So highlight number 1 about recommenders' latent ability. We're interested in how does this traditional top 10 evaluation matrix correspond to recommenders' latent ability. And we compared NDCG at 10 with recommenders' ability. And as we can see here, there is an obvious increasing trend. And this is also confirmed by the Spearman's correlation, which is quite high. However, if we separate these recommenders into 2 groups using the median of NDCG at 10, we found that the bottom half of recommenders there is still an increasing trend, and the correlation is still super high. However, for the top half of the recommenders, we observe that their ability kind of flattens as NDCG-10 increases, and the correlation drops a lot. Please note that this result is not only true for NDCG-10, but also true for all those quite popular metrics. We think this result is interesting because when we evaluate recommender systems, what we care about are those top models. And this result basically tells us that high rankings from those top evaluation metrics do not reflect high ability in modeling user preferences. And highlight number 2, we studied the difficulty and discrimination of the test sets. Here, in each figure, we plot the discrimination and the difficulty of the data points of test sets on movie lens 1 million and Amazon Books. Each data set is actually a user atom pair. So this is, we have this difficulty and discrimination from our aggregation procedure. If we look at the shape of these two figures, we notice that the highest discriminatory power lies in lower difficulty pairs, in user atom pairs, in movie lens 1 million. We also observe that in movie lens 1 million, there is a long tail of high difficulty and low discrimination user atom pairs. We think this suggests that in movie lens 1 million, there are some difficult user atom pairs that hardly any of the model can predict correctly. And we can also use to analyze the top 10 recommendations given by each model. For example, here the red dots in each figure are the top 10 recommendations from Atom KNN. We use Atom KNN as an example here. As we can see that the top 10 recommendation on movie lens kind of concentrated at lower difficulties. And lower difficulty means that these user atom pairs can be predicted correctly by many methods. So we think this suggests that the top 10 recommendations given by algorithms trained on movie lens 1 million kind of overlapped with each other. And conversely, on Amazon Books, we can see that the top 10 recommendations kind of covers the whole range of difficulty. We think this suggests that the recommendation given by algorithms trained on Amazon Books are more diverse. And highlight number 3, here we use user difficulty as an example, and we analyze how user difficulty corresponds to user engagement, which is denoted by the number of ratings given by a user gives. Surprisingly, we noticed that the user difficulty does not decrease as user engagement increases. Instead, it converges to a long-running average. And we kind of explain this as no user is an island. So which means that if we want to further improvements in recommendation performance, it would require like a large portion of users to increase their engagement level instead of just several users rate a lot of atoms. We also noticed that there are some less engaged users, but they still got quite low difficulty. And one reason we found is that if we look at these red dots, they represent users, and the atoms given by these users has also been rated by many highly engaged users. And we call this rolling stars. So basically it says that less engaged users can benefit from shared preferences provided by highly engaged users. To summarize a little bit, in this work we propose a novel methodology to apply IRT to recommender systems. And we showcase that we can use IRT to analyze or to understand offline recommendation evaluation from 3 aspects, namely recommenders' ability and the test set's difficulty, discrimination, and information. And we can also use IRT to analyze the characteristics of individual users and atoms. One thing I want to emphasize here is that these are just partial results from our paper, and I would highly recommend you to read our paper about more detailed discussion if you're interested, of course. I think that's all about my talk, and thank you for your time, and I'm ready to take questions. Thank you.
Thank you.
there are already questions on Slido. You can add additional questions and also use the microphone. I start with the first one. Someone saying, I've done work in the energy recommender systems domain with IRT, so using this similar approach. And the question is, but what do ability and difficulty mean in movies as you're moving? What determines difficulty?
Okay. So it's hard to say how does it mean in movies because we do not have such data to analyze such thing. But from evaluation perspective, I think the model's ability, as I explained, it's basically the ability to prioritize those higher preferred atoms over less preferred ones. Well, the atom difficulty basically means that how difficult those recommenders can answer this atom correctly, can recommend this atom to correct user, things like this.
Okay, thank you.
Yeah.
Another question. As AUC also evaluates the proportion that a model correctly ranks positive-negative pairs, it seems that there is some relationship between ability and AUC. Have you looked into that?
Yes, I think this is a good question. Yeah, I actually agree with this. There must be some relationship between AUC and also this latent ability. But one thing I want to emphasize is that IRT can provide us with some other perspectives, like towards these atoms, like, for example, whether it helps us to understand those difficulty atoms when we do evaluation instead of just opting this latent ability. Yeah.
Okay. Do we still have time? I ask one question because I'm curious.
Okay.
Read the paper and you mentioned that training the model is quite time expensive. So how long does it take to train the models for this RET?
Okay. So our training RT model is basically a Bayesian estimation. So as you can see from this, and we use mean field variational inference. And for Amazon books, which is the largest data set we used, it can take several hours, like about 5 hours, I guess. But for movie-length 100K, it still takes like 14 minutes. Yeah.
Okay, broad variety.
Yeah.
Thank you. Let's thank you again for the talk.
Thank you.